Our team members are Koki, Yuki, Koshiro, Bilal, and me, Kazuhiko, not Snoopy. So, and advisors. So, I'm going to give a general introduction and talk about mission design. The second, Koshiro will present our spacecraft subsystems and human factors. Finally, Bilal will explain our mission details, including risks, cost, and schedule. So, why is it difficult to go to Mars? As you know, Mars is very far from our planet. The mission duration is very long. Therefore, we must consider the physical and mental effects on the crew. Also, the technology available is amazing, but limited. And there is little time to develop additional technology. Third, the crew will be exposed to a high level of radiation. So we have to think about countermeasures. So here is a mission statement. Design a two-person Mars flyby mission that could be launched no later than 2024 as cheaply, safely, and simply as possible. From this, we developed our design philosophy with 6 ground rules. The crew will consist of 2 people. We must return astronauts to Earth in good health. We must use technology available by 2021 for Mars flyby opportunity, minimal cost, minimal complexity, and safety levels acceptable for humans. We also made 2 assumptions. First, SpaceX will have developed the Falcon Heavy Launch Vehicle and Dragon Crew Capsule by 2021. The second, NASA will have developed the Space Launch System Block 1B by 2021. By considering the mission statement, ground rules, and assumptions, we focused mainly on 3 important criteria: simplicity, cost, and safety. Here is our mission overview. Duration is 586 days. We'll use Falcon Heavy or SLS Block 1B. In the case of using Falcon Heavy, IMLEO is about 113 metric tons. In the case of using SLS, it's about 93 metric tons. The spacecraft volume is 74 cubic meters. In the case of using Falcon Heavy, the mission cost is about $6.5 billion. In the case of using SLS, it's about $7.0 billion US. For our mission design, we conducted trade-off study focusing on 3 factors: number of launches, number of powered flybys, and reentry method. We determined that the maximum number of launches is 3. The maximum number of powered flyby is 2, Venus flyby and Mars flyby. And there are 2 reentry methods, ballistic reentry or air capture. So as a result, the total cases are 12. In order to compare mission simplicity, we weighted each factor. The launches are weighted at 0.3, the number of powered flyby is at 0.2, and reentry method at 0.5. Case 1, 2, 3, 5, and 7 are equal or less than 1.0. In order to find a simple, cheap, and safe trajectory, we set 6 constraint conditions: delta velocity for Earth departure, for Venus flyby, and Mars flyby, minimum passing altitude for Venus flyby and Mars flyby, and reentry velocity. Based on these constraint conditions, the trajectory was computed. This shows the result. Although there are 3 launch windows, 2021 is the best for our mission for 2 reasons. First, its delta velocity for Earth departure and reentry velocity are smaller. The second, its payload fraction is larger. Combining the simplicity with calculation, we determined the 2 best options, case 3 and 7. Both use 2021 launch window, consist of 1 or 2 launches, have 2 flybys, and use ballistic reentry. This is our mission flow. This shows our orbit. We'll depart on November 17th, 2021. We'll fly by Venus on April 2nd, 2022, and we'll fly by Mars on October 12th, 2022. Finally, we'll arrive at Earth on June 26, 2023. Our time of flight is 586 days. And now that we've decided our mission flow, it's time to decide our launch vehicle and Earth reentry vehicle. So, as we've discussed, we'll launch once or twice. By considering payload to LEO, launch cost, and first operation year, there are 2 options. In the case of launching once, SLS Block 1B is the best. In the case of launching twice, the Falcon Heavy is the best. For ERV selection, there are 3 options: Orion, Dragon 2, and CST-100. In order to decide, we set 4 criteria: plausible manned flight by 2021, lightness, heat shield, and G-load. By considering these criteria, Dragon 2 is the best for our mission. This shows heat tracks and G-load during the ballistic reentry. Dragon 2 will be able to do these heat tracks thanks to its heat shield. As for G-load, the crew can endure because high G-load doesn't last for a long period of time. Now for the concept of operations. We suggested 2 mission options. This can increase the possibility for mission. This can increase the possibility of success for the mission. First of all, in the case of using SLS, we'll be able to launch once. By using the SLS, we'll launch TMI booster, MTV, Trans-Mars Spacecraft, and ERV into LEO. After that, by thrusting TMI booster, we'll inject spacecraft and ERV into Trans-Mars trajectory. They'll fly by both Venus and Mars, and they'll come into LEO again. Finally, we'll undock them, and by using ballistic reentry, we'll return astronauts to Earth in good health. On the other hand, in the case of using Falcon Heavy, we'll launch twice. The difference between using Falcon Heavy and using SLS is the first operation. That is, whether we'll conduct a rendezvous or not. After docking, we'll conduct the same operation with the SLS. And that's our mission design. So now, Koshiro will present our spacecraft subsystems and human factors. Thank you.
So thank you, Kaz. For the following subsystems, we apply the same selection style: simplicity, safety, and cost. We added other requirements to create a better trip for the crew members. Also, we took some precautions to avoid a malfunction of the spacecraft. Again, to be simple, safe, and efficient, the ADCS must be reliable, well-positioned, be able to change the strength of the propulsion, and strong enough to propel the spacecraft, and resistant to the radiation and high temperatures. Therefore, a symmetrical design of these systems is required. For the design of the ADCS, we adopted 3 star trackers, 12 sun sensors, and 3 inertial measurement units, plus 8 Super Draco thrusters, 28 low-power resistor jets, and 4 reaction wheels. These systems are based on the NASA MRO and the ESA Venus Express. And we adjusted for the high temperatures and radiation during the Venus flyby, where malfunction of the sun sensors can occur. Here is where IMUs and star trackers have a huge role regarding the spacecraft orientation. Layouts for the sun sensors is a key. We placed 4 on the sun-facing side of the service module, and 2 more on each other 4 sides. which makes an easy orientation for the spacecraft regarding the sun. Plus, we place them at a safe distance from the solar panels to avoid extra noise. Next, constant communication between the spacecraft and ground control is necessary, and the high band is better for our crew members to make a video communications. Adding to this, we thought about the high temperature near Venus, and we suggest dividing the bands to avoid the surplus of energy. For these requirements, we suggest one X-band dish antenna, one Ka-band dish antenna, and two MGA patch X-band. For the command and data handling system, 4 solid-state recorders and RAD 5500 powered computers will be installed to provide absolute performance and margins. Next, we chose the electrical power generation, storage, and distribution system that has already been used in past space missions because it is trustworthy and reliable. So what you see here is how our EPS and TCS were designed based on the changing solar insolation level. The spacecraft is the most insulated during the Venus flyby and the least insulated during the Mars encounter. And our power system has to support the electrical load of 7,000 watts in total. On to the actual design of the EPS and TCS, our design uses orbital ATK's ultraflex solar panels, lithium-ion battery system, and triple junction solar cells, which are used for the Cygnus spacecraft. Since Cygnus utilizes GS-USA's batteries, the same ones were used in this design. The battery system can support the electricity for 12 consecutive hours while waiting for the TMI on LEO and the Mars flyby. This system is reliable as these systems have had long-duration flight records with such projects as the JAXA Hayabusa, the Venus Climate Orbiter, the NASA DOME, and NASA MRO, and the ISS. Next, the TCS maintains the habitat and all electronic devices at appropriate temperatures. Since solar insolation varies drastically in our mission, both active and passive TCS will be used. The ATCS are designed based on the ISS ATCS, such as deployable radiators. Speaking of the PTCS, we will install 8 solar arrays. 4 of them are placed beside the service module, and others are placed beside the MPLM. To lower the heat load during the Venus flyby, we will store some arrays. To reduce the product of inertia of the spacecraft, for the attitude control system, we divide the area of solar panels into 8 and operate them 2 by 2. This will enable us simultaneously optimize the power generation and heat load. So this shows the actual operation of the solar arrays. Each line corresponds to the number of the solar arrays deployed. Before TMI, 4 of 8 arrays will be deployed. When close to Venus, 2 arrays will be stored. After the Venus flyby, as we get closer to Mars, 4, 6, and 8 arrays will be deployed respectively. After the Mars flyby, as we get close to Earth, we will store arrays 2 by 2. Next, the aircrew is critical to ensure the safe return of the crew members. As such, a highly reliable system with high redundancy is required. However, the e-crews must be relatively low mass and not take up excessive volume in the MTV. We conducted a feasibility study and concluded that the current ISS e-crews with 2 backup system and hybrid system is the best for design. Next, we move on to the human factors. To begin with, NASA's radiation exposure limit is 1,000 millisieverts during an astronaut's entire career. According to the research based on the NASA Curiosity rover, considering our mission is a 586-day trip, our crew will have received about 1,100 meal receivers. Furthermore, our crew will have received about 300 meal receivers during their 600-day stay in the ISS. So it is obvious that we have to take measures regarding this problem. To reduce the radiation below 700 millisieverts, the ISS has a wall of 10 grams per square centimeter. And our accommodation space has a wall of 20 to 40 grams per square centimeter. Next, the habitat affects the crew's physical and mental conditions. Regarding the habitat, safety first. Therefore, most of the supplies in the habitat are to maintain their health. The arrangement of interior spaces should provide for privacy, shown here as crew quarters and shelters, both which protect the crew from the radiation. Crew quarters at 20 grams per square centimeter, outlined in yellow, offer partial protection. And shelters with thicker walls of 40 grams per square centimeter, framed in red, offer more protection. Next, the daily schedule of crew members resembles the current ISS schedule. Please note, it is flexible. Now, we would like to suggest some out of the ordinary technologies. First, miso. The miso is a soybean paste originally from Japan and traditionally used in some meals and soups. There is research that shows the consumption of miso can make the human body more resistant to the radiation. Plus, the miso soup was approved as a space food, so we suggest its consumption as a crew preparation. Next, kaatsu. Kaatsu is adding pressure in Japanese, and it is an exercise method based on the blood flow restriction, which utilizes bands to adding pressure on the arms and legs. So using this method, the daily muscular training is more efficient. And we suggest its use because it is 1 kilogram each band, so it is light and useful on the long duration space missions. We suggest them as a counterpart of the medical risks. Finally, to conclude the subsystem descriptions, please look at the mass breakdown, designed considering simplicity, cost, and safety. Next, to describe safety analysis, details, and conclusions, please let me introduce my friend Bilal.
Thank you so much, Coach. So for the safety analysis, the design was almost complete, but we had a few questions. Is this going to work? Is this safe for the crew? Is the equipment good enough? Can the mission success? So with each phase of the mission, the risk for the crews and for the success. So we still have 2 proposals. That is why we have 2 sets of results. The total safety rate with and without assembly, which means by Falcon Heavy and by SLS respectively, are about 95.82% and 96.2% for the mission, and 99.23% and 99.24% for the crews. Both proposals are reliable, so let's continue with the details. To review our spacecraft design, for the habitat, we will use MPLM. For service module modified Cygnus. For the booster, in SLS case, we will use DCSS Enhanced. In case of Falcon Heavy, we will use Merlin 1D Enhanced. Radiator ISS, solar panel Cygnus, and the ERV, the Dragon 2. Next, here is the mass budget before the launch. By using rocket equation, we calculate propellant mass, then the sum of masses from subsystem, ERV, the whole propellant, and some margin. Our IMLEO came about 113,000 kilograms for Falcon Heavy and 92,000 kilograms for SLS. Simplicity, safety. Now it is time to address the cost. By using the advanced mission cost model as our estimation method, as it is appropriate during the early conceptual stages of mission, we input here quality, mass, specifications, IOC, block number, and difficulty we enter. So to calculate the entire cost, we first calculate development and production costs consisting of Dragon 2, modified MPLM, modified Cygnus. As a result, we have $5,399,000,000 for Falcon Heavy and $5,526,000,000 for SLS. Then we calculate the operation cost by inputting both the development and production cost in this equation with a TOF of 586 days. As a result, we have $944 million for Falcon Heavy and $967 million for SLS. Finally, considering the launch cost, in case of SLS, we have a total of $6,993,000,000. In case of Falcon Heavy, $6,537,000,000. The final detail is the schedule. We still have two proposals, so we have two deadlines. And both we have some deadlines for modifications, while the Venus and Mars flybys are both in 2022, while the crew will return by 2023. The only differences here is the launch and assembly by 2021. To sum up, we focus on simplicity, cost, safety, number of launches, number of flybys, and reentry methods in these two proposals. So we're using powered flybys in an Earth, Venus, Mars, Earth trajectory in 2021. We suggest the use of a SpaceX Dragon 2 for the return, while our IMLEO with about 100 metric tons, we suggest the use of Falcon Heavies for 2 launches or an SLS Block 1V for 1 single launch. Both of our proposals are reliable and are good. But if we have to choose today one, we will use the 1 single launch by SLS as our mission. However, it is important to be flexible. That is why we also present the use of Falcon Heavies as our plan B. Thank you very much.
We have time for just a couple of questions.
Questions?
Questions? Any questions?
Really? No question? No questions?
No questions.
Yes.
I noticed you're actually using some of the Hayabusa heritage, which is good to see.
Boosters?
Hayabusa?
Yeah,
Some JAXA.
in case of SLS, we were using DCSS Enhance. And in case of Falcon Heavy, we'll use the Merlin 1D Enhance.
No, the Japanese technologies.
Oh, Hayabusa, sorry, my bad.
Did you involve some of the latest technologies from JAXA? Hayabusa, they got a second mission happening.
Well, as you have heard in the proposal using JAXA, it is technology that it is reliable because it has been used. So we take the reliability to make it doable for the 2 flybys as a reference.
That's it. No, it's just.
Oh, okay.
All right. Thank you very much. Okay. So that concludes the presentations. The judges are now going to meet. I don't know if we should meet in a little room across there. Paul, okay, that's what we're going to do. Everyone else needs to leave this room because they're going to have to start setting up for the banquet. But before you go, I just want to make one point. We've just seen 10 presentations. In my view, all of them are feasible. Okay, these are 10 feasible ways to do a 2-person Mars flyby mission. by the year 2024. Okay, some of them may be a little better than others. That's why there's a contest. But as far as the feasibility is concerned, this has been proven. This has been now shown. Okay, we can have a space program that's really going somewhere. So I hope that some Washington people, you take this back up to the Hill with you and let them know. Thank you very much.
Well done, guys.